Discussion of the nearized this being to gravity. So that in the last lecture we discussed the general formalism, the equation of motion, and we talked about the action and the derivation of the energy flux in a plane wave. We also derived the point particle equation of motion. So now one thing that we can quickly see is the gravitational redshift in this new theory. To see, for instance, if you have the static gravitational field, how observers who live at different points in this field would detect, or what frequencies would they detect for the photons. Okay, so we are doing a spin 2 gravity linearized. And first we want to talk about redshift, gravitational redshift. So we want to consider some h mu nu field, which is, so this is a space-time diagram, and I have some h mu nu field that I want to assume to be time independent, to be static, and we want to consider some observer in this field, or two observers maybe. They send messages to each other, A and B. And then the question is that if A measures a sense signal with some particular frequency, with what frequency B measures it. Or we can ask if this field is localized and at infinity the gravitational field is 0, we want to relate the frequency of A to frequency at infinity. Once we do that, then we can also answer other questions. Okay, so now, how do we deal with this? We learned that if we live in this field, then if you look at, for instance, the point particle action, it looks like the point particle action that we wrote before, except that we have coupled to a different metric, G mu nu. So we said that if you have clocks which are microscopic compared to the length scale over which this h mu nu is changing, then we can just choose a different coordinate system, and in that coordinate system this becomes those rulers and clocks of that observer will measure just eta mu nu, except that not so they work naturally as if there is no gravitational field, but in terms of those new coordinate systems. Or in other words, we can introduce this tilde variable, this proper tilde proper time, which is minus g mu nu dx nu, and the good clocks are measuring working at fixed frequencies with respect to this tilde. So in other words, if I have someone who is at rest in this field, then I define some u tilde mu, the forward velocity, which is defined as we defined it before, except that it's dx mu divided by theta tilde. So it has the property that g mu, it has norm 1 with respect to, or norm minus 1 with respect to this metric g mu nu. And then asking about the frequency of the photon that is passing at this point. The frequency of photon as measured by this observer. This is of course a scalar quantity, and that scalar quantity is given by the inner product of this u tilde mu nu times k mu, where k mu is the for momentum of the photon. So this will be minus omega measured by A, where this u tilde is the this is the form velocity of observer A. Why is it the case? Because if we use a coordinate system in which this, in particular the time coordinate in which this metric becomes eta mu, then that u tilde mu for that observer becomes just 1, 0, 0, 0. So in that coordinate system, this object is just the zeroth component of the for momentum of the photon. But once we write it in this fashion, then we can calculate it in any other coordinate system. You don't need to go to that particular. Okay, so now, so we are almost done. First of all, since we have an observer who is at rest, we can determine, using this equation, we can determine what is u mu, so u a mu, or u tilde a mu, has only zeroth component. Sorry. So I want to plug this in here and assume that the observer that I'm considering is at rest. So what we have is that G00 times u tilde 0 squared has to be equal to -1, which tells us that u tilde mu is equal to 1 over the square root of minus G00 and 0. Of course, evaluated at the location of our observer. So this will be at location of xn. And then we need to know what is the form momentum of the photon, or in other words, if there is a photon which at infinity has frequency omega infinity, we want to see what would be its form momentum at the inside our gravitational field, when gravitational field is non-zero. And to do this, we should of course solve the equation of motion for a photon. So now this equation of motion for photon, we said that we can either derive it from some other version of point particle action, which is called the Polyakov action, or we can obtain it by taking the massless limit or ultra-relativistic limit of the equation of motion that we derived from a massive particle. In either case, the equation for the trajectory of photon looks almost identical to what we had for a massive particle, except that the tau tilde variable, which is proper time here, in the case of a massless particle, has to replaced by the affine parameter, some good variable that parameterizes the curve, because the proper length of the null curve is 0. So we need a better variable. So for photon we have, or for a null geodesic, we have the sigma g mu nu dx nu d sigma equals 1/2 d mu g alpha beta dx alpha d sigma dx beta d sigma. And what we call the momentum of the photon is related to the dx mu by d sigma. Dx mu by d sigma is going to give us the moment of the photon. Now, if we consider a static field, we can look at the mu zero component of this equation. So if we assume that d0 of h mu nu is equal to 0, then what we get is a conservation law from this equation, because if I look at the mu equals 0 component of this equation, I get 0 on the right hand side. So what we learn is that the k0 is conserved. Right? Where k0 is g0 mu times dx mu d sigma. So in particular, if I have a photon that at infinity had frequency omega infinity, so if k mu when x goes to infinity is omega infinity 1 1 or 1 1 0 0, then it's conserved momentum with lower index. When it's conserved frequency, covariant frequency is going to be minus omega infinity, and that is the same at every location, at all x. So k0 of any x, as long as the field is time independent, is going to be minus omega infinity. So now we are done, because now we know that omega of Alice is given by this expression, and the forward velocity of Alice, because she's at rest, is this, so it has no spatial component, it's just 1 over square root of minus g00 at her location times, so there was a minus sign here, I put it on this side, times the zeroth component of k, lower index, which we said it is minus omega infinity, so we get omega. And this is the square root of minus g00 at a location. Now this g00, of course, is nothing but minus g00. G00 is eta 00 plus h00, and this is the square root of 1 minus h00. And then we said that the H00 is related to the Newtonian potential by what expression? H00 is given by minus twice phi, the Newtonian potential. So what we get is that omega A is equal to omega infinity. And then we can do, since we are doing perturbation in phi, we are doing this linearized theory, then we can linearize this expression to get 1 plus omega infinity over 1 plus phi A. Well, I already did this square root because it was 2 and I took this square. So it becomes 1.
So you are doing the H small.
Yes, I'm working at linear ordering first. So this is nothing but omega infinity and 1 minus phi. So what happens is that if gravitational potential is always negative, because gravity is attractive. So if you have some frequency for the photon at infinity inside the gravitational field, the frequency is going to be higher. Again, the interpretation is easy. The photon has to spend some energy to climb up the gravitational potential. So it loses energy and has lower frequency and lower energy at infinity compared to when it was created.
In this whole framework where you are using linearized gravity, will you use the Photon metric or just Eton union to lower and Rayleigh indices? Not in this problem, but in general.
Oh well, I'm in general we use just atom union. If we don't say anything, we are using atom union to lower. So this union, at this one you should just think of it as a convenient tool to do the calculation.
But to lower and Rayleigh indices, you will use it.
Yeah, I always use atom union.
Can I use this argument to explain the CMB cooling, or is that a completely different effect?
Well, it's not. You can use similar arguments to explain it. It's not exactly this, and it's not completely different. When there you are dealing with time-dependent gravitation field, you are in cosmology, so things are time-dependent. So it's not exactly this, because here I'm working in a static field and I'm asking what happens for a photon that goes from inside the field to infinity.
But in some limit, I can argue that at some point of the universe, the field was very strong and now it's much weaker. The difference in frequencies is explained just for gravitational effects. So I can use this comparison for a static point first. Let's say take a time t at some point of cosmological history, and the frequency has certain frequency, and the difference with the frequency at other time in cosmological time must be different because of this.
Well, I'm not sure if you can. Maybe you can. I have, but it would be. Yeah, I don't have any simple explanation of that in terms of climbing out of the gravitation. Maybe someone has it and I don't know. Usually the simple understanding of why you have redshift in cosmology is because you have expansion of the space-time. And then the wavelength and frequency of the photons will be stretched in the expanding universe.
That's related to the change in the metric. It's also related to the change in the metric.
Yeah, but the difference is that here we are talking about the change in the metric in location, in a space, while there you are talking about the change in the metric as time changes. That's it.
But in that case, you have a non-zero energy density in the space itself, so you have omega, which you use in the Friedman model. The omega of energy is non-zero, but here you are just considering the presence of matter. Because you said that if the energy is negative, because the energy is negative due to the gravitation from the matter. But if you have energy in the space itself, then you have a positive energy density. So you have to incorporate that effect too, if you want to.
Energy. I mean, here also, like for instance, when we talk about having a gravitational field on the Earth, is because there is some mass distribution that produces this. In that sense, it's not too different. You have some positive masses here and some positive energy density there.
For example, if you talk about a single point particle, the metric that you get is completely different from the FRW metric that you get in cosmology.
Sure, yeah, they are different.
It's fair because K0 is not conserved in this case.
Right. Other questions? Yeah.
Can you choose a gauge such that the metric, at least H, is always time independent?
Is time independent? No. You might be able to do things at, for instance, some point or along some trajectory, for instance, but setting it globally time independent, no, there is no way of doing that. As far as I know. Yeah, I guess I'm almost sure that you cannot do it globally, but maybe in some region and for some. Yeah, maybe in some region you can do this. That I'm not sure. Okay, so then we can talk about gravitational waves. Which is now very easy to discuss after talking about dilaton waves. We basically do the same thing, except that there are some indices going around, more indices. So again, remember the question that we want to study is that we have some distribution masses which are moving, and we want to ask what is the faraway field, gravitational field, and in particular what is the flux of energy that is carried away by this. So we want to see that there will be the waves far away, whose amplitude dilute as 1 over r, decay as 1 over r, and then the energy that is carried in those waves will be something that we are interested in. Okay, so the way we did it last time was that we had this equation of motion for dilaton box phi equals minus 4 pi g times t. Here we have a similar situation, except the equation of motion for the metric is a bit more complicated. the state is a second order differential equation, and hyperbolic equation with the source on the right hand side is T mu nu, and that T mu nu is time dependent because the system that we are considering is time dependent. Now we just need to simplify that equation to be able to solve it, and to simplify it we use a gauge. Yes, we choose the I guess it is called radiation gauge, which is given by the following condition: the mu of h mu nu minus 1/2 eta mu nu times h is equal to 0. Where h is just the trace of h mu nu. Again, the index is raised by eta mu nu by the Minkowski metric. So you could ask, is it always possible to choose this or impose this condition? But remember, we had some freedom, some gauge redundancy of this formalism. We said that h mu nu can be modified, or can be transformed in this way, with an arbitrary, the same mistake, with an arbitrary function, set of functions xc nu, and so there are 4 of them here, and the question is, can we choose them such that these 4 conditions are satisfied? And the answer is yes. If you plug this in, so imagine if we start from h mu nu that doesn't satisfy this, so let me write it like h tilde mu nu equals to this. If we imagine that h mu nu does not satisfy, then this requirement for h tilde mu nu becomes an equation, becomes 4 equations for this x's, for these 4 x's. 4 equations for these 4 x's, the equations are, and the equations are basically similar to the equations that we had for the dilaton. They are of the form box x nu equals that object. So one can solve it, or maybe there's a minus sign here. So one can solve for these 4 equations using the method of Green's function. And then once we plug that solution here, that h tilde would satisfy this. So the choice is possible. And then I'm gonna drop this tilde, so I assume that I have done that, and then I call that new field that satisfies the condition just h mu nu. Also, let me call this object psi. So let's define psi mu nu to be h mu nu minus 1/2 eta mu nu times psi, where psi again is defined in a similar way. The psi. How does it work? Yeah, h mu nu minus 1/2 h psi. Thanks. Right, so we define this combination, and then the equation of motion for h mu nu in terms of the psi variable becomes extremely simple. It becomes just box psi mu nu equals minus 16 pi g t mu nu. Whose solution we can just write just copying from what we had for the dilaton, except that we just need to put the indices on top of it. So we had, so the solution becomes psi mu nu of T and R is equal to, so there was 4 pi g, now it's 16, so I get 4g integral and d3 r prime times T mu nu of T minus, so remember that here we had this retarded solution, r prime divided by r minus r prime.
Some minutes ago you said that if we set psi to have, or not psi actually, psi to have a particular value, then this condition can always be achieved.
Mm-hmm.
But if we add another psi such that box psi is equal to 0,
Yes.
then that can also be the case. There are
Yes.
so
There is a residual.
Yeah.
There is a residual symmetry that preserves this condition.
So that diffeomorphism can also change it. So what do we do then? Because it's not completely determined by that single condition.
Oh, sure. Yeah, that's something that I'm going to discuss. What happens is that we are actually looking at the particular combinations that are independent on or invariant under those residual symmetries. So that extra thing doesn't change the answer. Okay, so this is the solution, which now if we go to the wave zone, which is the part that we are most interested in, then again the same approximations are applicable. Here we can only keep the leading power in 1 over r, so we have 1 over r already. Anything subleading compared to that is irrelevant for the question of the energy flux at infinity. So those can be dropped. And therefore we end up with this expression, which again this can also be simplified, T minus r plus r hat times r prime and r prime. Okay, now so therefore we can solve for this given T mu nu. So conceptually the problem is basically solved. Given T mu nu, we know psi mu nu. Now question is, given psi mu nu, how do we determine the energy flux, for instance?
Sorry, how is that you can neglect the r prime in the denominator?
Why?
How is that the r drops out of the integral without the r prime?
Yeah, so first of all, we should keep in mind that we are talking about some localized system. So the idea is that you have a system.
So the integral is not over all the space, it's just over
It is, but the T mu nu is vanishing.
It vanishes outside.
So you have your sources that are near the origin, for instance, and this is the typical size here is that determines the range of this integration where the sources are non-vanishing, while you are looking far away, some point off.
Okay.
So of course you can expand in powers of r prime over r, or the size of the system over little r, the distance, but only the leading power is relevant for the question of what is the energy flux at infinity.
This only applies when T mu nu vanishes at very, very large distances as compared to It also means that the masses that we are considering cannot have electrical charge. Because if they have electrical charge, the electrical field itself has T mu nu. It vanishes, it goes to infinity.
Yes.
Okay.
Or this would be the answer when you neglect that contribution to the. So maybe they have it, but if that is a negligible contribution to T mu nu. Yes. So now we want to. Okay. So now the question is that what do we do with this? We want to calculate, for instance, the energy flux. So what we do is the following. First of all, we notice, as Muhammad said, there is an extra symmetry, some residual gauge symmetry here. So this condition hasn't fully fixed the gauge symmetries. We can use that to simplify h mu nu at far away point. So far away point, if you remember, this field will look like a plane wave, right? So to any observer who has some laboratory whose size is much smaller than the distance to the system, what that observer sees is just a plane wave that is coming from the system. So we want to simplify that plane wave. Then for that simplified plane wave, we can calculate the energy momentum tensor and energy flux, as we talked about in the last section. And then we want to relate that energy flux to this expression, so a bit simplified. Okay, so to do that, we basically consider the following. We first notice that there is this residual gauge symmetry. So we have h mu nu that can be transformed. This is the general transformation. But if we want to preserve that condition, then we see that we should have d mu of d mu xi nu plus d mu xi mu minus 1/2 eta mu nu times twice the alpha xi. Alpha has to be 0. So if we do a transformation, by the way, these gauge transformations, I think I never mentioned, or maybe I did. These are called linearized diffs, linearized diffeomorphisms, or linear diffs for sure. So if I do linear diffs which satisfy this condition, that gauge condition it remains unchanged, right? So what I've done here is just required that the change in this expression remains 0. So now what does this equation imply? This just implies that these two terms cancel, and this just tells us that box xi nu is equal to 0. So now, these are our residual diffeomorphisms. Now we want to consider a plane wave. So we are sitting far away, and there is this plane wave that is coming here. Of course, it's not plane wave everywhere, but it's a spherical wave, but at some small region it looks like a plane wave. So we want to take that h mu nu, which looks like a plane wave, so it has some amplitude. And then the phase goes as e to the minus I omega t minus k hat dot x. We want to use this residual diffeomorphism to simplify this. And the claim is that we can make this wave to be purely spatial, traceless, and transverse. So the statement is that imagine k hat, for instance, is equal to x hat, so in direction 1. Then by appropriate choice of these xc parameters, we can make this h mu nu. When I say we can make it, it means that I perform that transformation so that the new h hat mu nu will look like a matrix that has 0 everywhere except this block. Moreover, in this block it will be of this one. So in terms of equations, what it means is that if I define a 4-vector k mu, this is omega 1 and k hat, and another one k bar, which is omega 1 minus k hat. Then what we can do is to make k mu h hat mu nu equal to 0 and k bar mu h hat mu nu equal to 0 and h hat mu equal to 0. So this is called transverse. This is called traceless. When this condition is satisfied, it ensures that it is completely spatial and 0 everywhere except in some transverse plane, in a 2-dimensional transverse plane, because k and k bar fully span they span the extra direction. So the 0 and 1 in this particular case, for instance, the 0 and 1 directions are fully spanned by k and k bar. So when these two conditions are satisfied, h cannot have any component in the 0 and 1 direction. So it can only have components in 2 and 3 direction. That's what I'm writing here. Moreover, it has to be traceless. The fact that we can do this is not that hard, actually. Maybe I'll just say a few words about how we can do it. But before that, notice that once these conditions are satisfied, once it is a spatial, transverse, and traceless, then what it means is that if you have a direction of propagation, it only lives in the perpendicular plane. So it's since we are in 4 dimensions, it lives in a 2-dimensional plane. This h hat mu nu. It lives in a 2-dimensional plane, and it is symmetric, of course, and it is traceless. So symmetric traceless matrices that live in this 2x2 block there are only 2 independent choices for them, and that's what I mean by this h plus and h cross. So an arbitrary symmetric traceless tensor that lives in this plane can be expanded in terms of these 2 in this basis. So notice that these are basically related to the 2 helicities of the graviton that we were talking about. So the helicity plus 2 and helicity minus 2 just correspond to two linear combinations of these plus and cross polarizations. They are more or less like the relation is similar to the relation between linear and cyclic?
Circular,
yeah. Relation between linear and circular polarization of photons. Of course, another thing that you can see is that a 45 rotation acted on the cross polarization takes it to the plus polarization. And so this is fine. Okay, so now let me just mention why this is a possibility. It's easy because, so we have this plane wave and we want to perform this transformation to take this h hat mu nu to a particular form. Of course, this should have the same functional dependence on t and x, so that it accomplishes what we are interested in. So this should also be a plane wave, this xc. So this xc mu has to be something, some vector, xc hat mu times e to the, let me just write it as e to the minus ik mu, k mu x mu degree. And then the question is that, do we have enough parameters in here to make that choice, to make this possible? So what we do is that we take this xc hat mu, and then it's a vector, so we use all possible vectors, and we see that there is enough freedom to satisfy all of these conditions. So what we want is, so we expand it as, for instance, I write that A is an unknown coefficient, A times k mu plus B times k bar nu plus C1 times E1 nu plus C2 times E2 nu. So k and k bar I already defined there, and E1 and E2 take it to be two independent perpendicular directions to this k and k bar. So for instance, in this particular case, when k is along x hat, E and E bar are y hat and c hat. Now one can just by brute force make sure that these conditions are satisfied with an appropriate choice of A, B, C1 and C2. There are enough freedom to impose all of those conditions. Notice that the change of h hat under this transformation would be delta h hat mu nu equals I k mu x hat mu plus I k mu x hat mu. So it's some algebra question whether you can satisfy those conditions or not by the appropriate choice, and the answer is yes. Okay, so one other thing to notice is that these changes that set all of those components to 0 actually do not touch this block, right? Because they always contain a factor of k nu and k nu here. So when I perform this linear as diffs, I have never modified these components here. So that's what I meant when I said that this residual deformations are not going to change the part of the field that we are interested in. But when the field is brought in this particular form, then we know how to calculate this flux of energy momentum. This is something that we did in the previous lecture. If the field is in this simple form, then we can just take the action for this spin 2 field that we wrote last time. So remember, there was an action for H. The quadratic action for H was something like h mu nu epsilon mu nu alpha beta h alpha beta with an overall coefficient which was I think 64 pi g. So we first wrote it in the linearized, in the first order form. And then from there, if we impose this extra condition on the h mu nu, then the action, that action extremely simplifies. It becomes, let's say, like an action of a field in 2 dimensions, for which we can calculate the energy flux. So from this, we did calculate the energy flux, F, which was minus T01 or T0R, and that was given by 1 over 30 or minus 16 pi g times h plus dotted squared plus h cross dotted square. So this should be reminiscent of what we had from in the dilaton case. There it was 1 over 4 pi g phi dotted square. Here, because of different normalization, we get a different overall factor, but otherwise it's, and we have these 2 positive polarizations. So otherwise it's essentially the same thing. So basically, in order to calculate that flux, all that we need to do is to take this equation and look at that particular components, that transverse traceless, the spatial transverse traceless components of that this equation, and then plug it in the expression for the flux to get the energy flux, and then we need to integrate it over the whole sphere. So therefore we want to look at the spatial component of this side. Also notice that the difference between psi and h is gone because we made it traceless. So psi and h are the same thing now. So basically we want to look at, for instance, if we are if we are looking at the system in the x direction, we want to look at the components psi 2, 3 and components, which is this h cross, and components psi 2, 2 minus psi 3, 3. Okay, now there is another simplification. So therefore we decided that we are only going to look at the spatial component of that equation, the ij component. Now the ij components of this T mu nu can be simplified using the fact that we have a system which is localized. Since it is localized, then we can use the following manipulation. So if we have, using the fact that it's localized and it is constant, so we can write Tij equal to decay of xi tjk minus xi decay tjk. So now we can verify this, that this is correct, because if I act by this derivative inside, when it acts on decay on xi, it gives us delta of I and k, which gives us Tij. Of course, T mu nu, not of course, but I assume that it is made symmetric. But we don't have to make that assumption. Okay, so if I bring the derivative inside, either it acts on this x that gives me back Tij, or it acts on Kj, which is this expression I have subtracted. So this is correct. Now this expression can be, so first of all, this is a total derivative. So later on, when I plug this in this integral, since it's a total derivative and I'm integrating over the whole space, and since the sources are localized, that total derivative term becomes irrelevant. So I don't write it anymore. But this term can be rewritten using the conservation of T mu nu. So the conservation of T mu nu, d mu T mu nu equal to 0. That tells me that d0 T0I is equal to dk TKI. So this term can be written as minus xi d0 of T0j. Of course, I can take d0 away and then apply the trick the same again, the same trick again. I could also begin with symmetries with respect to I and j here. So this is d0 xi t0j, and this I can write as dk of xi xj times d0 with a factor of 1/2. So now I'm doing the symmetry search. So again, now if I act by this dk on xi, I get this expression. Not really. So let me symmetrize. Okay, now if I add by dk on xi, I get this expression. If I add by dk on xj, I get this expression. And if I add by dk on this, I get an extra term that I have to now add. That is d0 of xi xj dk of t0k, which can again be replaced using energy momentum conservation. So dk of t0k is d0 of t00 by energy momentum conservation, and this term is the total derivative, the spatial derivative. So again, we don't care about because we are going to integrate. So we have some other total derivative there, plus 1/2 d0 squared of xi xj t00. So the upshot is that as long as I'm interested in the spatial component of this equation, I can write it as psi ij equals 4g over r d0 squared integral d3 r. So there is the 1/2. Makes this 2, and then here, okay, so there I use x's, here we have r prime, so let's call them again r prime I, r prime j, t00 of t minus r plus r hat times r prime and r prime. And of course, I have dropped this total derivative thing. Okay, now one thing that we see is that if you remember in the case of the dilaton emission, we said that if you have a non-relativistic system, the expansion, the non-relativistic expansion, the expansion in powers of V becomes equivalent to the expansion in terms of spherical harmonics. Or in other words, we had a similar source there where the only dependence on R hat was coming from the argument, the time argument of the source. So there we notice that if we want to consider higher and higher spherical harmonics, we have to go to higher and higher time derivatives of the source with factors of R prime, so that is of the order of the velocity. So each time a factor of R hat is introduced, a factor of velocity is effectively introduced. So else, the spherical harmonic would start from else order in velocity expansion in terms of velocity. So here is the same thing. For a non-relativistic system, as we go to higher orders in this expansion, they will be suppressed by factors of it. In particular, the leading term in the expansion is just ignoring this, dropping that. And that can be written as a quadrupole moment. For non-relativistic system, remember that T00 is the same as the energy density or the mass density. So this expression that we have here is related closely to the quadrupole moment. In particular, if I want to look at the H plus and H cross polarization, say for instance we want to look at H YY minus HCC combination and work to leading order in this expansion in terms of velocity, what we get is 2G over 3R times Q double dot YY minus Q double dot ZZ, where Q is defined basically as before. Qij is equal to integral this 3R prime, 3R prime R, R prime J minus R prime squared delta Ij times T00. Okay, and similarly H. So you see there is the difference between these two, between this expression and this expression is that, of course, this factor of 3 that I divided by the other difference is this extra trace part, this delta Ij that doesn't exist there. But when I look at this difference, it doesn't matter, it cancels between the two. So when I'm interested in this difference, I can as well look at the quadrupole moment. Similarly, if I'm interested in the YZ component, that is given by 2G over 3R Q double dot YZ. Okay, so now what they can do is that for a general direction, we can derive these projectors into the two plus and cross polarizations. For a direction R hat, those projectors depend on R hat. They have to be perpendicular to that R hat direction, so they will change as I move. And then the general expression would be, the general expression for the flux would be 1 over 16 pi G now I have the square of that, 4 G squared over 9 R squared And then there will be sum over the two projectors, which I call them epsilon 1 and epsilon 2. So there will be epsilon S ij q ij triple dot square. And this factor is just g over 36 pi g of 36 pi r squared. And these projectors have the, let me just write the explicit form of these epsilons, so that you don't think they are not very scary. They are just basically the generalization of these to an arbitrary r hat direction. In this particular case, we have, say there is epsilon plus ij, which looks like 1/2 1 1 0 0 in the yz plane. So this is y, this is z, y, z. And then there is epsilon cross ij, which is 1/2. So there is a minus sign here. 0 1 1 0. And then 0 everywhere else. So they just project an arbitrary spatial vector or matrix in that particular, in those particular directions. So they are normalized so that epsilon s ij epsilon s prime ij is equal to 1/2 delta of s and s prime. And then they are normal to the r hat direction, to the direction away from the source. So r hat I times epsilon ij s is equal to 0. So for a general direction r hat, the sum over polarizations can be written explicitly in terms of delta ij and r hat. I'll leave it to you to check it. It's done explicitly in the notes. So we can.
But do you want to check?
No, just see that this sum over different polarizations can be expressed in terms of, well, basically this expression s sum over s equals 1 and 2 epsilon s ij epsilon s mn. This can be written. This has an expression in terms of delta matrices, the Kronecker delta, like for instance delta ij, delta mn, and many other permutations of indices and terms which contain r hat. So say r hat I, r hat j, and one delta and terms that contain 4 r hats, which is with some particular coefficients. So you can entertain yourself finding those coefficients. The fact that these terms can appear is just by symmetry. You can write just all possible terms that can appear on the right hand side of this equation. It can only depend on r hat and the unit matrix, which is this delta, and then fixing the coefficients is using this normalization condition and transversality condition.
When you say that at s is equal to 1 or 2, When you say S is equal to 1 or 2, so S is equal to 1 corresponds to plus or cross?
Yes, yes. One of them is plus, one of them is cross. Or any other basis that you like. So of course, in a particular direction, the flux that we get depend on that direction and the property of the source. That you can imagine, if I'm moving in this direction, then the flux that I send in X can be different from the flux that I send along Y or Z. So clearly, this F is a function of R hat and R, but the dependence on R is trivial. So now we want to integrate it over the full sphere, over all possible directions. So that dependence on R hat goes away. That one of the R squared also goes away when we integrate it over the full sphere. And from there we get the energy, luminosity, the rate of emission energy per unit time, which is the famous quadruple formula over 45. So this comes when so L is equal to R squared times integral d omega of f of R hat. So once we use this expression for the sum over the polarizations and then integral over all directions on the sphere, that gives us the final answer. Now you can see that this formula looks similar but not identical to the one from the dilaton gravity. So the overall coefficient is different, which means that these two have order 1 different in the prediction of the amount of energy loss, and therefore order 1 difference in the rate of change of the frequency of some orbital frequency of some binary system. So if there is a binary system that I measure very precisely how its orbital frequency is changing because it's losing energy to gravitational waves, then I can distinguish the spin 2 gravity from the spin 0 gravity.
Not 12 times. Because that was, I think, in the Diploma case it was 217 the denominator.
Yeah.
So this is almost 12 times larger. No, sorry, six times. So with that, a lot of difference.
Yeah. Although you should be very careful because the formula, in the dilaton case, there was also a monopole contributed. The subleading intended a monopole that I never wrote it down. If your system has some non-zero eccentricity, then that can also be comparable. But in any case, there will be some order 1 difference between the two results.